Okay, so things are a bit, okay, so everything seems to be working. No, this. So let's see. I should have been able to open a new note. And now I'll be able to write on it. You see this, blank white paper, yeah?
Yeah.
Okay, I'm gonna write on this. So,
wait.
please let me know.
Let me know when you're ready, yeah.
Yeah, I'm ready. So please let me know if things are not working. So, by the way, I'm going to talk about work with.
Okay, Alessio, let me introduce you. Yeah, it's my big pleasure to introduce Alessio Corti, who will talk about smoothing affine toric threefolds.
Okay. So this is work with Mate Philip and Andrea Petracci. And I'm going to talk about a paper that's on the archive. Okay, so this is well documented. And here's the plan for my talk. I'm going to talk about some context first. So this is a final search program. Then I'm going to discuss conjecture A. And then I'm going to discuss conjecture B. And then I'm going to talk about some outlook. Can you hear me well? Can you read well?
Yeah, we can. Yeah.
If you can face more towards your computer, then we'll hear you better.
Ah, let's try that. Maybe I can do this. Okay, so let me start right away with the first section. Okay, so final search. I wonder if I can perhaps even increase the volume a bit. Okay, there we go. So we want to. Sorry?
It's good now.
Great. So I want to talk about, so we want to understand mirror symmetry for final manifolds. Well, okay, I say manifolds, but I'm also happy with mildly singular. Perhaps actually more precisely, orbifolds is okay, not singular, orbifolds. And somehow I'm going to use this to do also classification. Of final. Okay, so these are, so here's some sort of meta statement that we have a lot of evidence for in several different contexts. And the meta statement goes a little bit like this. There is a one-to-one correspondence between some set of final manifolds taking up to deformation and certain Laurent polynomials taking up to mutation. So this meta statement is supposed to show both what's mirror symmetry and how you do classification. These two sets are one-to-one correspondence. So here maybe the final manifold is n-dimensional, and then the Laurent polynomial is in n variables. Okay, so that's it. And roughly speaking, the way this works is that you take a Laurent polynomial f, and then you form its Newton polytope P. And out of the Newton polytope, you build a toric Van variety. X sub P. And here the fan of X is the spanning fan of P. Okay, not the normal fan, spanning fan. Now, this toric variety is in general singular, and somehow the Laurent polynomial is supposed to also tell you how to make a smoothing of xp. And in all cases, this is how this correspondence works in this direction. You take f and you take smoothing of xp, that's the family, the deformation, the corresponding deformation pair. And so from this point of view, then the key question is, what are these certain Laurent polynomials? And I'm going to give you later a very precise idea of what sort of stuff this is in one particular context. And I suppose I just want to say one thing about...
Alessio, small question. Yeah. Does P contain 0 in interior?
Yeah. So I don't want to be too... I'm happy to be a little bit vague. In fact, most of the time it does, except that later today it will not, okay? Just... it's not so important, but if it is a Laurent polynomial, so I assume that there is a constant term, and so I know where 0 is. Let's just say that.
Thank you.
At this very general meta level, this is a detail. Okay. One thing that I want to say is that we are interested. I'm certainly interested in the theory of what mirror symmetry is and so on. But one key thing about the point of view here is that since I want to do classification, and that has to be done by large computer work, it's very important that we keep our data sets small. So we're not so much interested in elucidating all of the structure, the enormous amount of structure that comes from mirror symmetry, but to describe the small data sets that somehow encodes everything implicitly. Okay. At this point, I'd like to stop. And are there any questions? Because I mean, otherwise, does anybody want to ask a question at this point?
So far, there was only one. Okay. So there's a question in the chat. What does mutation means in this context?
I will tell you a case later, precisely. Okay, I'll be clear about this, at least in the specific context that we're going to talk about next. because one thing to understand is I do not see the chat line, and I don't know if
I will read. I will read all the questions in the
I'm
chat.
not sure there's a way for me to read it. I see my own screen that I'm sharing.
Alessio, don't worry about this. I will read the chat questions.
No, but I mean, see, I found a way to do it. It's I can't see it now. Yeah, very good. Very good. Excellent. Okay, so I'll continue, and I will make small breaks to ask for questions later. I cannot promise to constantly monitor the chat line. So anyway, this was the context. So now I want to describe conjecture A. So this is section 2. So let L be a two-dimensional lattice. You know, something as we move to Z2. And F in L a polygon, a lattice polygon. For me, these things are always convex. Now, I'm going to call N L plus Z. And I'm going to take the polygon F. I'm going to put it at height 1. The Z there is, I think of it being the Z axis. And I take the polygon and put it height 1. And then I take the cone generated by the polygon height 1, and I call it sigma. So that's a cone, that's a rational cone in N. And XF is the associated toric variety. So a spec of C M intersection sigma 2. So this is a toric variety with an action of the torus T equals spec CM. Okay, the conjecture A. So if you like, what this toric variety is, it is a Gorenstein toric affine threefold. Okay, so this X here is a Gorenstein toric affine threefold. Yeah. And conjecture A states that there is a one-to-one correspondence between the set of smoothing components.
Yeah.
I couldn't hear that.
Dan is asking if M is a dual of L plus Z.
Yes.
If M to this, thank you.
Home and Z. The
N or N plus Z?
L plus Z.
Oh, L plus Z. Yeah, yeah, okay, sure.
Smoothing components of deformation space of XF is in one-to-one correspondence with the set of normalized zero mutable polynomials F in KL with Newton F equal the polygon F. I will explain all of this, okay? what's a normalized zero mutable polynomial. It's just the message here is that it's going to be something easy from combinatorics. Okay, nothing terribly difficult in there. For now, let me just make a couple of remarks. So if XF has isolated singularities, then this is known. Then this is the work of Klaus Altmann. So it's very important that we allow non-isolated singularities, and the situation is very different there from the isolated singularity case. And so in general, when XF does not have isolated singularities, then I sort of point out this fact that the deformation space is infinite dimensional. But it turns out in this case in a very mild way. There are infinitely many variables, but there are finitely many equations. And each of them is using finitely many variables. If you know about these things, this is pretty clear. And so, I mean, in the end, the fact that the space is infinite dimensional is a bit of a red herring, okay? And the last thing I want to say is that this is the local case of fun search. So if we want to learn basically how to, the key step here is about the smoothing of a toric Fano variety, then a toric Fano variety, a proper toric Fano variety, then it's a, you know, union of, it's an atlas of affine pieces, and learning how to smooth the pieces is the first step in that direction, okay? And this is what Conjecture A is doing. So I want to tell you what's a normalized zero mutable polynomial. This will take some time. I'll give some examples at the end. So to make sense of the conjecture, I need to tell you what's a normalized zero mutable polynomial. So, you know, fix F polygon in this L. I will have examples, we'll have really concrete examples shortly. And we're going to work with Laurent polynomials. So F, I'm going to write it as a sum over L in F intersection the lattice of some coefficient monomial x to the power L. And here normalized means that for every vertex of F, then the corresponding coefficient is 1, okay? So this guarantees that the Newton polytope of F really is F, little f, big F. And, you know, from now on, there's always a fixed F, and all the Laurent polynomials are going to be normalized. So next, I'm going to tell you what's a zero mutable polynomial. But before I do that, I need to discuss what's a mutation. So here is
Alessio, and there's no condition on other coefficients?
For now, not, but there will be very short. So mutation. So I'm going to tell you what is a mutation. So to do a mutation, you need to choose an affine linear map phi from L to Z, non-constant. And then, so I denote by phi naught the linear part of phi, and I take a u, a primitive element in the kernel. Okay, there are two of these things. There's u and there's minus u, and please don't get bogged down in this. It totally doesn't matter. You choose one of them. And the fact I'm going to call h the Laurent polynomial 1 plus x to the u. Okay. Armed with this data, I can now discuss mutations. So let f be a Laurent polynomial. Sorry, I decided to use k rather than c. And so you can write f as a sum of terms f sub k, where k integer, and where f sub k, how to say this, the Newton of f sub k is contained in the level set phi equal k. Okay, phi being this affine non-constant map. And the mutation of f, when it exists, is defined to be, it depends on this choice of phi, sum h to the k f sub k. So this thing only exists if for k negative, h to the minus k divides fk. Okay. So it's a bit of a mouthful. Then let me do some examples. Okay, so you see that this is actually nothing to be afraid of. The examples. I'm not going to ask you if you have any questions at the moment, because I don't expect you to have understood this unless you already know it. But let's do some examples and see whether the situation improves. So I'm going to write, consider, for example, this polygon here. This is F. Okay. And it doesn't really matter where the origin is. So those dots there are points of the lattice, right? And it doesn't really matter because I use the mutation data is this affine function phi. In the end, it doesn't matter where the origin is. But you see, you could imagine that the origin is right this corner here. And so this would be then the constant term. And then this point here would correspond to the monomial x, and this thing to monomial x squared, and then x cubed, for example, and then this would be y, and then y squared, and then this dot here corresponds to x times y, and so on. So now I'm going to write some numbers. I'm going to put down some numbers that correspond to the coefficients of those monomials inside f. So, you know, I write here 1, 2, 1, and I write here 2, 3, 3, 1. Okay. So perhaps I am now going to erase these monomials because they are just creating unnecessary confusion. Okay, and I just leave the sorry, I just sort of wonder if I look at my screen, I see this bit of Zoom chat here. Do you see that too?
I don't see the Zoom chat, no. I
Okay.
mean, I minimized it, so I can see it.
No, very good, very good. And I'm just sort of, it's a sort of meta question that I'm having, which is what exactly do you see of my desktop? Okay, and you know, that's not a completely trivial question. You obviously don't see all of it, but I'm happy with your answer. Okay, that's okay. Don't worry about it. So now I have this. So this polygon with those little numbers that represents a particular Laurent polynomial. Okay. And let me try to mutate it. And so to mutate it, I need to choose an affine linear function. And I'm going to choose an affine linear function. I'm going to put it in, I don't know, in yellow here. And I'm just going to tell you what are the values of this affine linear function. So on this bottom line here, where these 1, 3, and 1 are, I choose it to be, I don't know, at level -3, okay? Or why don't I just do -2? Okay, phi equal -2 on these guys, and then phi equal -1 on these guys, and then phi equal 0 on this guy, okay? Then I'm supposed to choose a primitive element, as it said here, u in the kernel of the linear part, and then form the polynomial h equal 1 plus x to the u. And the h here is going to be, h is 1 plus x, okay? Remember that this was the constant term, then there was 3x, and then 2y, and 3x squared. And so h is 1 plus x. Then I'm supposed to write f as a sum over k and z of fk. And so here the f will be f minus 3 plus, sorry, minus 2, f minus 2 plus f minus 1 plus f 0, where f minus 2 is simply going to be 1 plus 3x plus 3x squared plus 1. F minus 1 is y times 2 plus 2x, and f0 is y squared. I just take the bit of that polynomial which lives on that level set, okay? And then the mutation of f is, by definition, sum h to the k f sub k. And so, for example, I have to start from f minus 2, and I have to divide by 1 plus x squared. So f minus 2 divided by 1 plus x squared plus f minus 1 divided by 1 plus x plus f0. And so what is that? 1 plus 3x plus x plus 1 divided by x squared is just 1 plus x. And then that's 2y. And then nothing happens there, plus y squared. Okay, so then they mutated, so this is mutable, and the mutated, the mutated polynomial, I represent like this. Okay.
Alessio,
Yes.
could you repeat how you got 1 plus x as h?
Yeah. So I have to look at the kernel of phi, okay? And so the kernel of phi is or phi 0. The kernel of the linear part is just this this red line here that goes through 1, because I decided to put the origin there. It really doesn't matter all that much. And so then a generator, see, curve phi 0 is generated by the vector 1, 0, okay, plus or minus 1, 0. That corresponds to the monomial x. And then I'm supposed to take 1 plus x. Okay, that's my h. Does that make sense?
Yeah.
Then
What was phi 0 again?
the linear part. So, you know, the level sets are all translates of the kernel, basically. There's the level set phi equals 0 somewhere. And, you know,
Okay.
now we're, yeah, okay. It has to go through the origin, and I decided to put it there. So, I mean, yeah. So let me do another example, maybe a little bit quicker. Same Newton polygon. So I'm going to write 1, 3, 3, 1, 2, 1. But here, instead of putting a 2 there, I'm going to put a 3. Okay. Yeah. And now I'm going to choose a different phi. I'm going to choose a phi that put this vertical line here at level phi equal minus 2. And I'm going to choose that vertical line at phi equal minus 1, this one at phi equals 0, and this one here at phi equal 1. Okay. And the mutation is going to take this vertical polynomial 1 plus 2y plus, now here the h is going to be 1 plus y. Okay. And so the first vertical polynomial 1 plus 2y plus y squared is going to be divided by 1 plus y squared. And when you do that, you just remain with coefficient 1. The next one, the next vertical bit is going to divide by 1 plus y. So you're just left with 3x there. Nothing happens here. Okay. And then the last vertical line is going to be multiplied by 1 plus y. So actually, this is what you get. That's the mutation. Okay. So the polynomial, the earlier polynomial with a 2 there was not mutable by this mutation, because the 3x plus 2xy is not divisible by 1 plus y. Okay. So this first polynomial is not mutable by the second mutation, and similarly, the second polynomial is not mutable according to the first mutation. So that's one thing there. And let me do a third example. Perhaps I want to choose F. So now this polygon here. And so I'm going to write 1, 3, 3, 1, 3, 6, 4, 3, 3, 1, and 1. And there's a very nice mutation here where the bottom line, I put it level -3. This one here, I put level -2. This one here, I put level -1. And this one, I put level 0. And the mutation, so the bottom polynomial is going to be divided by 1 plus x cube. And so nothing is left. Then the second, f minus 2 is going to divide by 1 plus x squared. That one will be divided by 1 plus x. Nothing happens there. And if you just give it a moment's thought, this is the mutated polynomial. Okay.
Alessio,
Yes.
small thing, technical. On your screen, there's a volume control just in the middle of the screen. So sometimes when you write, you cannot see what you write. It's in the very middle of the screen. I don't know.
And how do I get rid of that?
I don't know. I have no idea. So I never saw Mac basically in my life. So.
Oh, I think it's gone now.
Yeah, it's gone. It's gone.
I don't know how I did it, but it's good. It's good to. It's good. Okay, so now here's the definition of zero mutable. If a polynomial is a product of two polynomials, then this thing is zero mutable if and only if both f1 and f2 are zero mutable. And then the other one is that f is zero mutable if and only if the mutation of f is zero mutable. This is a sort of inductive definition. You perhaps have to start by the notion that the constant polynomial, okay, perhaps I should throw something else in, otherwise you are not going to go anywhere. The zero step is that the constant polynomial is zero mutable. Maybe that's also not enough. I just say that any monomial for all L in L, x to the L is zero mutable. So these three rules determine exactly what the zero mutable polynomials are. Let me sort of try and clarify this. I mean, if f is irreducible, then f is zero mutable. Well, perhaps I should have given this as a definition now in retrospect. If and only if there exists a sequence of mutations that takes f to some f0 to f1 all the way to a finite sequence of mutation that takes f to a monomial. So somehow f disappears under a sequence of mutation. Sorry. So all these polynomials that I gave you are zero mutable polynomials, and perhaps you can figure out what are the next mutations that you need to do to make them disappear, become just, you know, monomials. Okay, so all polynomials above. So, you know, I'm sorry, I could have, there are certain things that we know about zero mutable polynomials. they're very easy, given a polygon F, they're very easy to enumerate. And they essentially corresponds to -2 curves on the cluster surface. There are, some very different equivalent, several different equivalent descriptions of what zero mutable polynomials are. And I do not have the time to tell you the whole story. So I just gave you the most basic combinatorial definition that I can. We know a lot of these things, and they're rather elementary, but take quite a while to go through them. So I'll just show you this and move on. So are there any questions at this point?
Not in the chat.
Okay. Now, I sort of wonder now if, so, perhaps I can go back to this. The conjecture A, if you remember, states that there is a one-to-one correspondence like this between smoothing components of the formation space and normalized zero mutable polynomials. And I wonder if now, let's see. So if I do this, do you now see a Emacs window? Hello? Somebody saying.
Yes.
Excellent. So I just sort of prepared this little demonstration. This is a Macaulay 2. Okay, I'm going to do Macaulay 2. So the second polygon that I gave you, and the corresponding third. So here I'm going to make the. Okay, let's see if this works. So F. Okay. I actually need to first start Macaulay 2. Yes. And let's see if this is going to work. So I'm going to make, so there are 3 zero mutable polynomials on that polygon, of which I've shown you just one. Okay. Now I'm going to make in Macaulay 2 the corresponding toric variety. So, it's got a binomial ideal that you can see there, and the resolution is 14 by 35. This is a typical, every codimension, if you practice these things. This is a codimension 5 Gorenstein ring, and they all have 14 generators in the ideal and 35 syzygies. And I just have to do something here. And then I feed it to this program that was written by Nathan Ilton, which computes the versal deformation space. Now, it normally takes just a couple minutes to do this one here, but I'm afraid that now, because there is lots of other things switched on in my computer, then it will struggle with it. I get a little message. My computer just sent me a little message that says, performance reduced due to heat. And it says, closing zoom.us may help your Mac cool down. That's exactly the one thing I don't want to do, close zoom.us. So, it's working. Okay, so it's finished the calculation. Now it's spitting out all this output here. I really don't know why. And there must be some way of turning. It will go on for another couple of minutes doing this. And, I'm not, there must be some way to switching that off. But, I'm lucky enough that I was able to switch the computer on. You cannot ask me to be able to switch it off as well. I mean, I'm soon enough it will be done with this dribble, and we'll be able to see what we get. The point that I want to make is that we have tested this conjecture rather extensively using this little computer thing, okay? And it looks good, right? Namely, we obviously did not find any counterexamples to it. Now this is getting a little bit tedious. It should be done quickly, but it's okay. I can joke for another minute max. And if not, we'll just continue the talk and go back to this thing and see the final result. It's beginning to look human. I really don't know why it's doing this. The output of this program is the equations for the deformation space and also for the universal family. So we are supposed to see that there are 3 smoothing components in the deformation space because we found 3 zero-mutable polynomials. And so we also need to check the generic fiber is smooth. But we can do that because the program outputs also the equations of the universal family. Yeah, okay. I'm beginning to give up. We'll give it another few seconds. I did it before and it only took 2 minutes. And it's fascinating to watch this, this stuff happening on the screen. Maybe I should just let it be. We'll come back to it. We'll leave it working there, and because there are a couple of things that now everything is frozen. Okay. That's all right. So hopefully now you can see that I was writing. Maybe I want to tell you briefly about Conjecture B. So Conjecture B. Very quickly. So the aim here is, again, you fix some polygon F in L, and you also fix some zero mutable F. And then you take M sub F to the corresponding component of def X. And for technical reason, I want to take deformations of the pair X toric boundary. There's not much of a difference between this and deformation space of X. And the aim here is predict the tangent space to MF at the origin as a torus, as a rep of the torus. Okay, so I want to know how it splits in irreducible representations. And basically okay, so now note that mutations of F are in terms of these affine maps from L to Z, but that's just the same as the linear maps of L sum Z to Z. And this is just M, so that's characters of your torus. So these mutations are also certain characters of the torus. And the way the conjecture B works roughly is that if F is phi mutable, F being this fixed Laurent polynomial, zero mutable. If f is phi mutable, then phi is an element of M, and then I'm saying then phi is a weight that occurs in the representation of the tangent space. It's pretty natural. So you only need to correct this a little bit, and I'll just tell you very quickly how you need to correct it. So in fact, let me just say it. Conjecture B. So the dimension of, I look at this tangent space at the origin, and I look at the part of weight M, where M is an element of the character group of the torus. And this dimension here is 1 if indeed F is M mutable. Okay, then it is n sub k, which is the number of prime factors of f of multiplicity k. In fact, multiplicity larger than equal k, if M is the vector 0, 1, okay, and 0 otherwise. Okay, so that's conjecture B. So to conclude, let's see if, yeah, let me do the conclusion. I said it was going to look some outlook. Okay, so in terms of outlook, then we, and it is me and many collaborators, I don't want to try to list them all, we are working on similar conjectures, conjectural statements for the following situations. In the local case, we want to generalize to, well, you want to do the Gorenstein, but dimension 4, okay? And we also want to do Q Gorenstein. And in the global case, we want to do Fano threefolds, global Fano threefolds. Then, but Gorenstein, but also non-Gorenstein Fano threefolds, so Q Fano threefolds. And then, of course, Fano fourfolds. And this is going to take a little bit of time, but the point here is that I am, I think this stuff is just going to work. And for each of these classes of Fano objects, there will be some nicely described, easily dealt with combinatorial class work. Then we are also working on software implementations for all these things. In various aspects of them. And then finally, let me discuss a little bit about where we are with the theory. What's the hope of proving things like this? Can we prove conjecture A, for example, the one I just told you today, or B? Okay, so the first step would be to just construct families X to MF where, you know, MF is something whose tangent space is predicted by conjecture B, as predicted by conjecture B. And so we construct families, and then we don't necessarily know that these are smoothing or that they are a whole component of the deformation space, or let alone all components of the deformation space. But let's at least begin with constructing this family. And the methods for constructing them, I know two. One is log geometry, where we break your toric variety down in certain pieces, and then you put some log structures on it, and then you try to use the methods of log geometry to smooth the stuff, okay, to construct deformations. And the other one is, in principle, more powerful, and it is the intrinsic mirror symmetry program, but not as developed as yet, where starting from the Laurent polynomial, you construct some space, and then you look for some log Gromov-Witten theory, and then those rings, those log Gromov-Witten theory rings, are just going to be literally, you take the proj of those rings or the Riesz construction of those rings, and you get your deformations out of that. And so let me stop there. That was already a little bit over time, but not too much, and I did start a little bit late. Let's have a look at the, oh yeah, so it finished, okay? So it finished, my colleague finished his thing, and now let me decompose the ideal. Okay, let's see. You see how nice it is? It's got three components, and they're all smooth, okay? So, and it's true that they're also smoothing components. I'm done. I can stop sharing my screen and maybe take questions if there are questions. You can please, I saw Ragni Pina, she showed her face, and that was very nice of her to do that. Maybe she had to leave, and if she did leave, then it's very lovely that she showed herself. Thank you, Ragni. Yeah, no.
Okay, Alessio, thank you very much.
Yeah, thanks.
Yeah, thank you. Any questions for Alessio?
And please show your face if you're around, whether I know you or not. It'd be nice to see you. So give me a little bit of emotional support, okay? The thing about these talks is that you leave and you don't even know whether there was an audience or not out there.
It's a good lesson for our seminar. Maybe we should do this all the time.
Do what? Of showing the face?
Faces. Yeah.
Yeah. I think it's I think it's, yeah, I like to do that.
So hi, Alessio.
Hello. I couldn't believe it. It's very nice. You look good, man.
Thank you. So are you finding new Fano threefolds actually? Threefolds?
Yeah. Yes, we are. You know, you can play this with for Q Fano threefolds. Of course, smooth Fano threefolds, we already know them. But if you do for Q Fano threefolds, then there are many cases where you look at a Hilbert function, and you don't, it's a putative Hilbert function, and you don't know whether there is a family there or not. And so we can feed our Laurent polynomials in it, and the program will spit out the finite remaining Laurent polynomials. And then we can actually construct by computer the deformations in the way that I showed. So at the moment, it's very laborious, and it doesn't always work because there are bugs in the software. But if you have a Hilbert function and you want to know how many families of Q phenotypes are there, then you can contract us out, and we'll be able to tell you in a few weeks. Okay, that's more or less the status right now for Q Fano threefolds.
More questions to Alessio?
Hello. People don't want to ask questions, but why don't they want to show their face though? Come on, let me see your faces. I'm not going to tell anyone. Hi, very good. Bert, Carolina, yeah. Ragni. Very nice. Yeah.
Okay, if there are no more questions to Alessio, let's thank him.
Okay, thank you all. You have a good day or evening.
Thank you, Alessio.
All right, you got me. Yeah. Very good, Mars. Yeah. Yes.
My internet is not stable. I just was kicked out because maybe everyone opened the faces. I think it's.
Yes.
Yeah, Lisa, thank you.
Thank you very
Yeah,
much.
so
It's been nice to be here. And perhaps I can now go. But thank everybody for showing up.
Thank
And
you.
for all those
Yeah, I will upload the video today in
okay,
1
very
hour.
good. Okay. Thank you. Goodbye, everyone.
Bye.